Hi, welcome back. This is, I think, now the 13th lecture of the lecture series. We were discussing Hartree-Fock when we left off, and we're going to begin by applying Hartree-Fock to a standard example, which is a very useful and general example, which is the translationally invariant interacting Fermi gas. So what we're imagining in our head is describing, for example, electrons in a metal, but we're throwing out the details of the underlying crystal lattice, so we don't have any ions breaking the perfect translational invariance, thinking that these are not going to be very important for the physics we're going to be interested in. So it's just the electrons in the system. Now, this actually has a little bit of a problem due to the basically due to the fact that the Coulomb interaction is long range, and the problem is as follows: if you start with a vacuum, nothing in it, just vacuum, and you start adding lots of electrons. We're not going to put in any positive ions. We're just putting in lots of electrons. Well, the problem is that the energy of this it's divergent. It's infinite with the size of the system. It blows up because you have all of these negatively charged electrons all repelling each other without a positively charged background neutralizing it. So in order to get rid of this unfortunate divergence, what we often use is for Coulomb, if we're going to be considering Coulomb case, we often use a uniform positive background, a uniform neutralizing plus charge background, which gets rid of this divergence which gets rid of this divergence associated with all the electrons repelling each other. This model of having interacting charged particle interacting fermions like electrons with a uniformly charged uniform background is known as the jellium model. Jellium, I think it's spelled like this, or maybe jellium. That doesn't look as good, but okay, let's keep it like this. Jellium model, and the term was coined by Conyers Herring, who was a very important solid-state physicist in the middle of last century. Conyers Herring was the head of the famous Bell Laboratories theoretical physics research department, which included people like Phil Anderson and Walter Cohen and lots of extremely important physicists of last century went through the Bell Labs theoretical physics department. It was started by Conyers Herring, and very frequently Conyers Herring, his influence was on much of the work where he wasn't actually a co-author, that he would suggest problems for people to work on, and they would be very important problems, and he had very good sense for directing people to important problems, and he's often acknowledged in some of the most important papers as having suggested that someone work on this particular problem. Anyway, so he was the first head of the Bell Labs theory department in a rather unfortunate twist of history, when Bell Labs was closing down many years later after it had lost its its stature as being the greatest lab on Earth. I was actually the last head of the Bell Labs theory department when it was shut down. For whatever that's worth, it's a rather dubious distinction, but I'm stuck with it. Anyway, so when we use a Coulomb interaction, sorry for that long digression, when we use a Coulomb interaction, we're going to use a uniform neutralizing positive charge background to get rid of this the divergence of having all these negative charges interacting with each other. Another possible route to controlling this divergence is just consider a short range interaction V of r between particles. Now, that's not appropriate for electrons because electrons have Coulomb interaction, but it is appropriate for example, helium-3, EX helium-3 fermions, which do interact with each other via a short-range interaction, and also possibly for cold fermionic atoms if one is interested in cold atom physics. So either one of these is a good way to control this problematic divergence. So just to remember what we were doing last time, we have our Hamiltonian is our single particle piece and our interaction piece. And the single particle piece is going to be the usual kinetic energy, but for a translation, there's going to be no trapping potential. It's just going to be the usual kinetic energy in a translationally invariant system. It'll be sum over k and the spin sigma, h bar squared k squared over 2m k squared, c dagger k sigma, c k sigma. K is a vector, I guess, for a three-dimensional system. Okay, so that should be easy enough. So it just counts the number of fermions, either 0 and 1, in a particular orbital k and sigma. So with wave vector k and spin sigma. And if it's occupied, if c dagger c gives 1, you get energy h bar squared k squared over 2m. Pretty easy first term of the Hamiltonian. The interesting term is the interaction term, h int, which we'll write in this form I guess we had yesterday. We'll write it as k1 sigma 1 k2 sigma 2 k3 sigma 3 k4 sigma 4. Yesterday we just wrote a b c d, and here orbital a is going to be the orbital with k1 and sigma 1. B will be k2 sigma 2, or maybe we call it alpha beta gamma delta. Then there's this v coefficients, which I'll write as k1 sigma 1 k2 sigma 2 k3 sigma 3 k4 sigma 4, and then it will be c dagger k1 sigma 1 c dagger, I'll try to make this a little clearer, k1 sigma 1 c dagger k2 sigma 2 c k4 sigma 4 c k3 sigma 3 sigma 3. And again, notice the switch in order of these two operators compared to these indices. The definition here, there we go, the definition here, so you can see it, v k1 sigma 1 k2 sigma 2 k3 sigma 3 k4 sigma 4 is defined as the two-body state k1 sigma 1 k2 sigma 2, then the interaction v of r minus r prime, k3 sigma 3 k4 sigma 4. Okay, just the inner product matrix element, which we can write out in all its glory if we want. It's delta sigma 1 sigma 3 delta sigma 2 sigma 4. The Coulomb interaction, we're only going to consider interactions which do not flip over spins, so it's diagonal in spin space. Dr integral dr prime 1 over volume. I'll try to remember to draw volume as this sort of big V with a cross across the top so it doesn't get confused with V, the interaction. V squared. Then we have the state K1, K2 here is e to the minus I. Okay, this is the bra, so it should have a minus K1 dot R1 plus K2, K1 dot R, the 1 plus K2 dot R prime, and then the ket will be e to the I K3 dot R plus K4 dot R prime, and then the interaction of R minus R prime. Okay, now because this is a translationally invariant system, the Fourier transform simplifies quite a bit. We can write it in the following way. Okay, we still have this matrix element just ends up being a Fourier transform since we're working with plane waves K1, K2, K3, and K4. So we have delta sigma 1, sigma 3, the same delta sigma 2, sigma 4, 1 over the volume of the system. There's a momentum conserving delta function that the momentum of K1 plus K2 better be the same as the momentum of K3 plus K4. The interaction conserves the total momentum, and then we'll write it as V twiddle of K4 minus K2, but K4 minus K2 is also the same as K1 minus K3. Good. And I think that is that's all we need here. So with that way of writing the matrix element, I can simplify this H int up here into a slightly nicer form, perhaps, allowing these delta functions to act, allow this Kronecker delta function to act, and my H interaction will then be 1 over 2 times the volume of the system, and we'll sum over, I guess, K1, sigma 1, K4, sigma 4, and Q, C dagger, K1, sigma 1, C dagger, K4 minus Q, sigma 4, C, K4, sigma 4, C, K1 minus Q, sigma 1, and then V twiddle of Q, where V twiddle is the Fourier transform of the Coulomb interaction, or whatever interaction we're considering here. So as long as it's a V of R minus R prime, it could be short range, it could be long range, doesn't matter so far. We just Fourier transform it to get V twiddle. Okay. Now this form for H int here is equivalent to something else which might be a little bit more obvious. It's equivalent to 1 over 2 times the volume of the system, sum over all Q of rho of Q, V twiddle of Q, rho of minus Q, and then normal order, where rho of Q is sum over K and sigma of C dagger, K plus Q sigma, C, K sigma, which is just the Fourier transform at wave vector Q of the density operator psi dagger of R, psi of R. If that much isn't obvious to you or doesn't look familiar, it might be worth going through this Fourier transform and convincing yourself that that what we've written here is true. So it's really just this interaction term is the interaction between a density at one position, a density at another position via the Coulomb interaction, and then you Fourier transform the whole thing such that you can write in K space as a sum over momenta Q. Okay. Now we're going to work with we're not going to write things in terms of rho of Q. We're not going to do so often. We're going to work with this form. So let's copy that, use it again, copy, use it here, paste, amazing. Love how that works. Okay, so beautiful form for H int, and we're not really going to work with Feynman diagrams much, but it is useful, particularly for people who grew up with Feynman diagrams, to write a diagram occasionally because one reason is because you'll because other people do it. Just because other people are doing it doesn't mean you should do it. But at this level, okay, for doing really complicated calculations, it's handy sometimes to write Feynman diagrams to keep track of your perturbation theory. For many calculations, what practicing physicists actually do is they actually do the calculation explicitly without writing down a single diagram. You just write out the perturbation series or whatever calculation you're doing without writing a diagram, and then at the end of the day you might write a diagram because it's sort of it's a shorthand notation for what you did that you can show someone on a slide or in a paper, which conveys the same information as a lot of detailed calculation, which you probably don't want to show them. Okay, so anyway, this complicated looking interaction here I can write as a diagram as follows. A diagram like this I'll write like this, and then an interaction here, Q going along there, an interaction here, like this. So this is K4 sigma 4 coming in, K1 sigma 1 going out, and K4 minus Q sigma 4 coming out. Draw that arrow better. This is coming out. And going in is K1 minus Q sigma 1. Okay, let's see if we can figure out where these terms. So Q is going this way up the squiggly line, and Q is K4 minus K2, or is the same as K1 minus K3. So if we look at this term, so this interaction vertex, let me draw a box around this maybe. I can distinguish it. Okay, good. So this interaction term here, it destroys something at K4, destroys something at K1 minus Q. Here they are. Destroys something at K4, destroys something at K1 minus Q. They're coming in, they get destroyed, and then what comes out is something's created at K1 here, and something's created at K4 minus Q here. Okay, so this diagram represents this interaction, and V occurs at this wave vector Q, which is the momentum transferred between those two density vertices here. Okay. Now, in Hartree-Fock theory, you'll recall that the general scheme is if you have 4 fermion operators, we want to take the average of 2 of them and leave the other 2 unaveraged. So let me just write out these, maybe I'll just copy them again. Write out these 4 terms here, these 4 fermion operators here. Oops, copy, and put it down here, paste. Okay, I'm not interested in this thing here. Okay. All right. So here are my 4 fermion operators, and if I have a choice of which 2 of these I want to average and which 2 of these I want to leave unaveraged. So if I average this one with this one, that gives me a direct term or a Hartree term. And if I average this one with this one, that will give me an exchange term or a Fock term, direct Hartree. And this one will give me exchange or Fock. Okay, so we can describe that diagrammatically as well by simply closing up when we average 2 of these vertices, we are just closing up this diagram. Either this guy gets closed up here, or this guy gets closed up here, and I'll draw those diagrams in a moment. But taking the average is closing up these lines with each other, so that you only have 2 remaining lines, one creation and one annihilation operator, and you've taken an average over 2 internal lines. Okay, so for people who like Feynman diagrams, you'll understand what we're doing. All right, so let's start by assuming the state we're considering is a Fermi C. Okay, so we have to consider what is the Slater determinant we're considering. So we'll write that as Fermi C. We'll justify this post facto later on, and the Fermi C is the product, I guess, over spins up and down, product over k less than some kf, C dagger k sigma on, draw that again, k sigma on the vacuum. Okay. Now, if we, okay, maybe I should write out the int again. I copy this one more time. This, copy this one more time. Oops, copy, and write it out again. Paste this. Okay, good. And I'm not interested in this. Now, if I want to take the Hartree term of this Hamiltonian, Hartree, maybe H Hartree, I want to take an average of two of these terms, say the first and the last here. And so that will give me 1 over the volume of the system. We lose the factor of 2 because there's two ways in which I could have made this average. The first and the last, and the second and the third, they'll be equivalent. Then we have sum over Q. And what I have averaged is the sum over K1 sigma 1 average of C dagger K1 sigma 1 C K1 minus Q sigma 1. That's averaged. And then what's left over is the sum over K4 sigma 4 C dagger, looks like an E, C dagger K4 minus Q, I guess with sigma 4, and C K4 sigma 4, and then V twiddle of Q. Okay, now what's crucial here is in this expectation value, I have the state I'm considering is a Fermi sea. If I destroy a fermion from the Fermi sea, in order to get a non-zero expectation, I have to put it back in exactly the same place. So there's no way that this can be non-zero for any Q which is non-zero. So this thing here is a delta function, Kronecker delta, with a Q being 0. And then the value of this is going to be, well, you'll get 1 for each possible value of K and sigma in this sum. So it will just give me the total number of particles in the system. So that means that H Hartree, so it's fixing Q to be 0 here, and H Hartree is then number of particles in the system divided by the volume of the system, V twiddle at Q equals 0, and then sum over, I guess, K4 and sigma 4 of C dagger K4 sigma 4 C K4 sigma 4. If we wanted to explain what we did using our diagrams, we would have drawn something like this. We have K4 coming in and K4 coming out. The Q is at 0, and we average. We had two legs coming up here, and we connected them up. We took an average of them to get this bubble. Gives me this bubble here. It gives me just this density factor. Okay. So what is this? What is the physics of this term? The physics of this term is nothing more than a chemical potential. This is just counting the density again. This is going to be an operator that measures the density. Here we took an average of the density, counted the total number of particles in the system, and this is going to be an operator that's going to just measure the total density in the system. So this ends up being just a chemical potential shift. This is a chemical potential shift. Chem potential shift. And in fact, if we're using the jellium model, where there's a background positive charge at Q equals 0, that will exactly cancel the interaction term at Q equals 0, and this term will just drop altogether. So the effect of the neutralizing positive background is to cancel the Q equals 0 term of a V twiddle, and that kills the Hartree term altogether. If you don't have a neutralizing background, or if you have short range interactions where there's no reason to have a neutralizing background, it will just end up being a chemical potential shift, which generally isn't very interesting. So let's look at the exchange or Fock term. So again, let's see if I can. Okay, it's not going to allow me to. I'm going to have to cut and paste again. So let's take the interaction again, the interaction term again, cut and paste it yet again, copy and paste it here, paste. Okay, and then we want to write down the exchange term, H exchange, and this is more interesting. This has a minus sign. Exchange terms always have a minus sign. 1 over the volume of the system, sum over K1 sigma 1, and sum over K4 sigma 4 and Q. We'll write this now C dagger K4 minus Q sigma 4 C K1 minus Q sigma 1 V twiddle of Q, and then times C dagger K1 sigma 1 C K4 sigma 4. Okay, so this one's much less trivial here. This thing can be non-zero for lots of Qs. However, in order for this thing to be non-zero, K4 has to match K2, and sigma 1 K4 has to match K1, and sigma 1 has to match sigma 4, because you start with a Fermi sea over here, you destroy something in the Fermi sea, and then you have to put it back to get back to the ground state again. So this term here is delta sigma 1 sigma 4 delta K4 K2, and it also should be a Fermi function of I guess K4 minus Q, that this Fermi function, that if you try to destroy someone above the Fermi surface, well, you can't do it. You can only destroy things that are below the Fermi surface. So in other words, this factor here, this Fermi function factor, is 0 or 1, depending on whether, well, maybe I'll write it as this, NF of K4 minus Q equals 0 if K4 minus Q is greater than KF, and is 1 if K4 minus Q is less than KF. Okay? KF. Okay, for me. Okay? Good. So the way this is typically written, this exchange term is typically written, this whole term on the inside here is summarized in one object, which is called the self-energy, and including the prefactors here. So I'll just rewrite this. I'll try to move myself out of the way. I'm always getting in my own way. So H exchange is sum. This is a sum over K and sigma, and this is annoying notation, but the self-energy is usually written as a big sigma. So this guy here is a summation sign, the big one, the big sigma, whereas this one, sigma Fock, is a symbol indicating the self-energy of K. Sorry about that, but that's the notation that's always used. Sigma Fock is the self-energy. It has a value, it's a number of K, and then C dagger K sigma C K sigma, where sigma Fock is going to be all of this stuff with this one sum left over out front. So let's just write out sigma Fock. This is minus 1 over the volume of the system. It will be sum over Q, V twiddle of Q, the interaction in Fourier space, and then the Fermi function, which requires that K minus Q is less than KF. So write that. K minus Q, absolute value must be less than KF. Okay? Okay, so now I can put myself back up in this corner. So in diagrammatic notation, we've connected, we had I'll draw it a little bit sideways, we had something that looked like, this, right? And we're connecting it up now like that instead. Something like this. So, or in other words, it's usually drawn this way, where Q goes along the interaction line, and this is K coming in, K minus Q, K, like that. That's what the self-energy looks like diagrammatically. Okay? So putting all of this together, we have everything together here. We have H Hartree-Fock is then going to be the sum over K and sigma. There's the h bar squared k squared over 2m, just the non-interacting part, that's h naught. There's density times v twiddle of 0, that's just the charge at q equals 0, the Hartree term, n being density total number of the total number of particles divided by the volume. And again, that term is canceled if you have a neutralizing background in the jellium model. And the interesting part is sigma Fock of k, and then c dagger k sigma ck sigma, which we can write as sum over k and sigma, energy Hartree-Fock of k, c dagger k sigma ck sigma. Okay, very simple form. Now this is kind of special. What we just discovered. What we've discovered is that our Hartree-Fock Hamiltonian is diagonal in k and sigma. It's fully diagonal. Now remember, when we derived Hartree-Fock, our rule was that we would calculate the Hartree-Fock Hamiltonian, and then we'd rediagonalize it, and then we'd go back and we'd recalculate the Hartree-Fock Hamiltonian, plugging back in to recalculating the expectation values, recalculate the Hartree-Fock Hamiltonian, and iterate until we reach convergence. Now, in this case, we converged on the first iteration because we discovered that our Hartree-Fock Hamiltonian is already diagonal. Okay, and that might seem surprising. We basically guessed, by guessing a Fermi C ground state, we guessed the right Hartree-Fock ground state, and the only thing the Hartree-Fock is doing is it's giving a modification to the energy as a function of k. Now that it might seem surprising that we've managed to guess the right ground state at the first iteration, and we didn't have to iterate Hartree-Fock self-consistently until convergence. But in fact, it's not so surprising when you think about it a little more carefully, because we have something very, very powerful, which is the translational invariance. So the translational invariance is something that guarantees that our system is going to have to be momentum eigenstate, and in fact, all of the excitations, at least, are going to have to be momentum eigenstates as well. And since Hartree-Fock can give us not only the ground state and can also give us all the excitations, each one of these excitations has to be labelable by a momentum. And that's going to constrain us to have a situation where our Hartree-Fock Hamiltonian is going to have to be a sum of terms, each one which has a definite momentum corresponding to a particular orbital. And the only thing that the Hartree-Fock Hamiltonian is doing is it is giving us a modification of the energy of each orbital, and this self-energy term depends on the occupancy of all the other orbitals. Now, this is also interesting for another reason, that the Hartree-Fock, since we started with this conjecture, back here, that the ground state is just the simple Fermi C, and what we did by calculating the Hartree-Fock Hamiltonian is we basically just calculated the expectation value of the Fermi C, the expectation value of the interaction in the Fermi C ground state. Now, that is exactly what we did in first-order perturbation theory as well. So the result, at least in this particular case where we have a translationally invariant system, the result of first-order perturbation theory is going to match exactly the result of Hartree-Fock theory, because the best Slater determinant that we can possibly write down is exactly the filled Fermi C that we used in first-order perturbation theory. Okay. Now we can go on. We can find some features of this Hartree-Fock ground state. So let's find the total energies associated with these different terms. Maybe if we use a jellium model, we can drop this one altogether. So the only let's keep them for now. So the total energy, let's calculate total energy, total E. There's the kinetic term. This is an exercise that we assign our students in second year Stat Mech. to show that the energy of a filled Fermi C is 3/5 the total number of particles times the Fermi energy. If you don't remember how to do that, it might be worth reminding yourself. The energy, the Hartree energy, is, the Hartree energy is, well, it's just 1/2 the n v twiddle 0 times the number of particles in the whole system. So it's just this term times 1/2 the number of particles in the whole system. And the Fock energy, E Fock, is just going to be the sum of the self-energy over all the occupied states in the system as well, which we can write out, remembering what the form of the Fock term way up here is with the potential at Q times the Fermi factor at Q. The energy of the Fock term is 1/2 volume of the system. Then it will be sum over Q and Q prime, the Fermi function of Q, the Fermi function of Q prime, and v twiddle of Q minus Q prime, where the Fermi function is 0 and 1, depending on whether a Q or Q prime is greater or lesser than the Fermi momentum. Okay. Now the only thing that wasn't maybe obvious is where these factors of 1/2 come from, and that's the 1/2 that we discussed when we talked about Koopman's theorem. That when you calculate the energy, you need to, in Hartree-Fock, you need to insert a 1/2 so that you don't overcount the energy of particle 1 interacting with particle 2 and then recount it in the particle 2 interacting again with particle 1. Okay. Now remember that for most metals, fermionic systems, where our interest is at temperatures which are low, or energies, consider energies or temperatures or T, which are much less than the Fermi energy. I mean, the Fermi energy of your typical metal like aluminum is 10,000 Kelvin or some enormous number like that. So we're interested on very small energy. So it's nice to expand our situation of interest around the Fermi surface. So in the case of a non-interacting fermion gas, the energy of a state K near the fermion energy is exactly the Fermi energy plus expanding the dispersion around the Fermi surface. We get, H bar absolute K minus Kf, where this prefactor here is known as the Fermi velocity. Right? This you should remember from your second year stat mech, just expanding the K squared around the, or from your solid state course, it's expanding K squared around the Fermi energy gives you the energy at the Fermi surface plus Vf times the momentum difference from the Fermi surface. Okay. Okay. Now in the interacting case, HF interacting, we can write an effective mass or an effective Fermi velocity. Ek is going to be Ef star. This is the sum renormalized Fermi energy plus we'll write HKF over M star H bar K minus Kf. Again, we can always expand around the Fermi surface, and the way we generally do that is we write H bar squared over M star is d squared by dk squared of the Hartree-Fock energy as a function of k. Okay, so this is just saying that we can take those interactions, find this energy as a function of k, now having the interactions in them, the Hartree-Fock energy, this energy here, E Hartree-Fock, I guess it's this whole thing here. Maybe I should label this whole thing as E Hartree-Fock, E HF of k. So we wrote it here as well. We can always just expand that guy around the Fermi surface to get an effective mass. Now in helium-3, for example, where we don't have this this problem associated with long-range Coulomb interaction, maybe I'll even write this down. For helium-3, m star ranges from 2 to about 6 times the bare mass of helium-3, and depending on the pressure and temperature on pressure that you're working at. So the renormalization of the mass can be extreme. It can be very strong renormalization of the mass, entirely due to interactions. Now, since we're mainly interested, everyone's still good. Give you a rest there. I have a tendency, even in lectures, to move on very quickly without giving you a chance to stop and think. But here, since it's video, you can always pause the video. But I should probably give you a chance to stop and think anyway. Just tell a joke or something. But I don't have any jokes about effective mass. I don't think I do. Anyway, I'll tell you though that this lockdown thing, it's definitely changing my effective mass. That I find that I eat a lot more and I don't actually, my gym is closed. Don't get to exercise as much. Anyway, let's consider the case of Coulomb interaction. Did I just make a joke about effective mass? I think I did. Interaction. Case of Coulomb interaction. So we'll write V of R is the usual E squared over 4 pi epsilon naught R. Then let's try to calculate the effective mass, or write down what it would be. Well, first we have to Fourier transform it. Integral dr e to the minus I k dot r e squared over 4 pi epsilon naught r. That's e squared over epsilon naught absolute k squared. So this is okay. You should know that in 3 dimensions, this is a 3-dimensional integral. Just by dimensional analysis, you know it's going to be proportional to 1 over k squared down here. This is a k squared. Try this again. K squared, absolute k squared down there. And you know there's going to be an e squared up top and an epsilon naught downstairs. I guess what's not obvious is that the prefactor is 1. It's sort of an exercise in doing the Fourier transform. And we do have the unfortunate feature that v twiddle at k equals 0 is divergent. But this is exactly, this gets cancelled by neutralizing background, by jellium background, by positive background. Okay, so we don't have to worry about that. So the interesting thing to do then is to calculate the Fock energy if we want to find the effective mass. So the Hartree-Fock energy, but the interesting part is the part that comes from interactions. The Hartree part is going to be canceled entirely by the neutralizing background, neutralizing. And so the part that's going to affect the effective mass is the Fock term. So let's write the Fock energy. Sigma Fock of K is minus 1 over the volume of the system, sum over Q, V twiddle of Q times the Fermi function of K minus Q, which guarantees that absolute K minus Q has to be less than KF. Okay, so this is what the Fock energy is, and it's maybe not so. Okay, so let me plot it. It's going to look something like this. So this is absolute K on this axis, and this is 0 here, and this is going to be sigma Fock on this axis. And I guess it's not too hard to calculate this really quite easy to calculate this at k equals 0. And I made a little exercise to do it. The value of this is, I guess, 2e squared kf over pi, I think. I think I have it correct in the notes. I'm not sure the type notes. I'm not absolutely positive in my written notes I have this number right, but I can check it in the handwritten notes. And then we have kf here. And this drops as you get to higher q, and then drops algebraically here. And what's not obvious until you do the calculation is the slope is log divergent here, divergent at kf. You have a log divergent slope at kf. And a log divergent slope at kf means the effective mass goes to 0 at kf, okay, logarithmically. So this is a problem. It's not physical, actually. It's an error of the approximation, and it comes from something we neglected in our calculation. Maybe I'll first tell you what it is we neglected. What we neglected is that over long distances, the other electrons in the system screen. Maybe I'll write this. Neglected screening. What do I mean by this? Okay, so if we want to know the interaction between two electrons, which are some distance away from each other, you just say, well, it's the Coulomb interaction. But when you consider those two electrons living in a soup of lots of other electrons, if you imagine putting a charge in a metal, we know what happens to a charge in the metal. It gets screened by the flow of other charges in the metal. So the other electrons come in and screen that charge to make its influence very short-ranged instead of long-ranged, which is what we get if we just consider the bare Coulomb interaction. So there's some big collective effect whereby if you have one electron sitting here, the other electrons sort of bunch near him to destroy his long-range Coulomb interaction, or they move away from him, I guess, so that the positive background can neutralize his. Somehow I'm making them all male. Okay, so so you have this electron here, maybe a female electron over here, and a male electron over here. They're both the same kind of electrons. They're identical, but I want to make. Okay, I won't give them a gender. So you have an electron over here and another electron over here, and this electron is screened by its friends in the sense that they move slightly away from the electron in the middle, such that the neutralizing positive background neutralizes the charge of that electron into that area, and from a distance slightly further away, you can't even see that there's a charge there, so that the effective interaction can be much, much shorter than what we usually think of as Coulomb interaction. So in the next lecture, or the lecture after, we're going to spend a lot of time thinking about this screening effect, which is something that's important for us to understand. But before doing that and before moving on, I want to show you or prove roughly that the Fock term really does have a log divergent slope at kf. So let's write out the Fock term again, just to try to get this right. Okay, let's write out the Fock term. Sigma Fock of k is minus 1 over volume, sum over q, v twiddle of q, and Fermi of k minus q, which we can rewrite as minus e squared over epsilon naught, 1 over the volume of the system, sum over, is k prime less than kf, and then 1 over k minus k prime. So I shifted this sum such that, I shifted this sum such that q is k minus k prime, and k prime is k minus q. Maybe I'll write that k prime was k minus q here. We can turn this sum into an integral, which is, I guess, convenient. E squared over epsilon naught, integral 0 to kf, I guess d3k over 2 pi cubed 1 over k minus k prime squared. So this is the expression that we want to evaluate, and it's pretty obvious that if let's see, so it's actually integral to k prime, isn't it? Integral to k prime. So it's fairly obvious that for large k, this is going to decay, which is what we drew up here. For large k, this will decay eventually. But the thing that isn't obvious is the log divergence at kf. So let's try to show that. First of all, I'm going to throw away these prefactors. That's not interesting. Let's imagine that we're here's part of my Fermi surface, so part of a big circle here. Okay, and I'm going to put my fermion close to the Fermi surface here. I'll call it at k, and just for simplicity, I'll put it in the x direction. So this is in the x direction here, close to the Fermi surface. So we can rewrite this integral here as integral. We'll write it as dk prime x. So it's going to be taking k prime in the x direction, and then dk prime in the other two directions, which I'll write as dk prime perp, and then 1 over k minus k prime squared. And I guess dk prime x, we know k prime x has to go, I can take that k prime x from minus k Fermi to k Fermi. And then k perp here will go, k perp will go only out to, I guess, from 0 to, I guess, square root of kf squared minus k prime x squared. So it's basically integrating over disks, successive disks here. So that's a disk at some particular k prime x, like this, and this is a disk, and we're trying to integrate over that disk here. So we rewrite this integral dk prime x from minus kf to kf, and then I'll write this integral is going to be k prime perp dk prime perp, and then there's I guess a 2 pi because it's radially symmetric. So this is the usual, take a two-dimensional integral and write it as r dr, 2 pi r dr instead of d vector. So I'm going to radial coordinates in the perpendicular direction, and then this denominator here is going to be k minus kx prime squared plus k perp squared. Okay, well, we can do that integral, and 0, we'll write this just to call it cut off up here. So we can do that integral, and it gives us a log. So there's a 2 pi, there's an integral from minus kf to kf dkx prime, and then what we get from that integral is log of k minus kx kx prime squared divided by the cutoff. And if we do that integral, we then get k minus kf log k minus kf plus correction terms associated with the cutoff. So d energy dk is then log of k minus kf, and d squared energy dk is 1 over k minus kf, which goes to infinity, and that is my log divergent effective mass that we get in Hartree-Fock approximation. Okay, so the next lecture, actually, I'm going to take an interlude. I'm going to do the other exam problem from last year, because the other exam problem focuses entirely on Hartree-Fock, and then in the following lecture, we'll discuss screening of Coulomb interaction, which has an awful lot of interesting physics in it, and screening and response. And there'll be just a couple more lectures to go with the on the examinable part of the course, and then we'll go on to BCS theory, which is not required but entertaining. So hopefully you'll spend your isolation during the coronavirus listening to things for entertainment, including BCS theory. Okay, anyway, I'll see you next lecture.